sight becomes story.
See better, shoot better, create better.
You got the camera, now get the vision. Shoot with purpose, create with vision.
Creative vision, creative vision.
This is creative vision, where sight becomes story.
Like ocean waves, electromagnetic waves have crests and troughs. The crest is the highest point of the wave, and the trough is the lowest point. The center between the lowest and highest points is called the mean position. The distance from the mean position to the crest or trough is called the amplitude. This is the height of the wave. An amplitude is measured in meters. The distance between two consecutive crests or troughs is called the wavelength, which is also measured in meters. Its symbol is lambda. A crest and a trough together make up one wave cycle. If one wave cycle passes through a point in 1 second, the time period is 1 second or 1 hertz. If 10 wave cycles pass through a given point in 1 second, then it's 10 hertz, which is called the frequency. The number of wave cycles passing a particular point in 1 second is its frequency. Consider 3 electromagnetic waves traveling at the same speed. Since the speed of these 3 waves is the same, the number of wave cycles crossing a point per second would vary. For example, if the first wave cycle is long, fewer wave cycles will pass per second compared to the other 2 waves. So the first wave has a low frequency, while the third wave has a higher frequency. This means that a longer wavelength has a lower frequency and a shorter wavelength has a higher frequency. But how do electromagnetic waves have different wavelengths and frequencies? We know that electromagnetic waves are produced by the acceleration of charged particles. But not all charges accelerate or vibrate at the same rate. If a charge vibrates slightly, it produces lower frequency electromagnetic waves. If a charge accelerates rapidly, it produces higher frequency electromagnetic waves. So the intensity of vibration determines the frequency of an electromagnetic wave. Given electromagnetic waves, wavelength, and frequency, we get the speed of light. The speed of light never changes. The wavelength and frequency are directly related to each other. All electromagnetic waves carry energy, and the amount of energy depends on their frequency and amplitude. The higher the frequency, the more energy. The lower the frequency, the less energy.
Let's look at the properties of waves. Waves have measurable properties, one of which is frequency, wavelength, and amplitude. Frequency tells us how fast the wave oscillates. Wavelength is the distance between the peaks. And the amplitude is how tall the wave is, which in light translates to brightness. So when we're talking about light in photography, we look at brightness as amplitude of the wave. To visualize this, you can use a rope, wiggle it slowly, and you get long waves like red light. Red light is the wave at the low side of light. And it's very important to understand this. If you wiggle it quickly, you get short, rapid waves like blue light. So this is another secret. We're going to cover some of this thing later. That blue light is a light at the high end of the light spectrum, visible light spectrum. So what does it mean? If I shine a red light and a blue light, one of them has more power, the blue light.
Where sight becomes story.
See better,
Now get the vision. Shoot with purpose, create with vision.
Creative vision, creative vision.
This is creative vision.
Evidence of electromagnetic waves. Now, how do we know that light belongs to the family of electromagnetic waves? Let's look at the evidence that convinced scientists. Part 1. Maxwell and Hertz. Now, James Clerk Maxwell mathematically predicted electromagnetic waves in the 1860s. Heinrich Hertz later confirmed this by producing and detecting them with sparks. The link between electricity and magnetism was no longer theory but a reality. Part 2. The electromagnetic spectrum. Light is just a small window in the vast universe, or in the vast spectrum of electromagnetic waves, which we call the electromagnetic spectrum. At one end, we have long radio waves, then microwaves, then infrared, then the visible light, and then ultraviolet light, and then we have the X-rays, and finally the gamma rays. Your remote controls uses infrared light. Medical imaging devices uses X-rays, and your cameras, yes, your camera sees only the visible side, which is between 400 and 700 nanometers. Now we are talking about the wavelength of the electromagnetic wave. So what our camera captures through our lenses are electromagnetic waves that are between 400 and 700 nanometers. Do you know your security light captures something lower than this? Yes. It can capture someone at night in the dark, and it's able to recognize people. It is using the infrared signals. It is using other parts of the electromagnetic wave spectrum. So you see, it's not just only the visible light that can produce an image of something. Think about the X-rays when you go to the clinic, a medical facility, and that X-ray machine is put on you. What comes out is a picture. That picture is the image produced by X-ray, just like the image produced by cameras, are produced using visible light. Part 3, why it matters for photography. Now, camera lenses or camera sensors are designed with filters that block most infrared and ultraviolet light to keep our images natural. So be careful when you take away some of those filters that block most of this infrared and ultraviolet light from your lenses. When you buy some lenses, you discover that you find another lens on top of your lens, and you can actually go buy filters for your lenses. Let me see if I can grab one by the side of my table. So this is an example of a filter. Now this particular filter is adjustable, so you can use it for different kinds or different diameter of lenses. So this filter out ultraviolet light, infrared, and more than that.
To visualize this better, I'll bring in a short demonstration from another video.
Add a pane of glass. Nothing happens. When the glass is removed, it discharges again. Some types of ultraviolet light are blocked by glass.
However, remove those filters. Now the filters are like this. If you remove those filters, and you can capture surreal infrared landscapes or UV fluorescence. Specialized photography uses the whole spectrum. For example, astrophotography. They capture X-rays from the stars with space telescopes. The proof that light is an electromagnetic wave is all around us, from radio signals to the photos you capture every day. We'll explore the wave nature of light more in our next lesson.
Creative vision, where sight becomes story.
See better, shoot better, create better.
You got the camera, now get the vision. Shoot with purpose, create with vision.
Creative vision, creative vision.
This is creative vision.
Hertz and the wave nature of light. Let's see an opening shot of camera lens, then transition to a graphic showing light waves. Hello everyone, welcome to our new episode. Today we are diving deep into the fundamental nature of light, the very essence of photography and cinematography. We'll explore how light works, not just as something we see, but as a complex physical phenomenon. Our journey begins with a pivot figure, Heinrich Hertz. Now they say when purpose is not known, abuse is inevitable. That is why we are studying light, because the understanding of light and its nature will help us become better photographers, cinematographers, and videographers. Now, Heinrich Hertz, whose groundbreaking work laid the foundation for understanding electromagnetic waves, including light itself, because light is part of it. His discovery of the wave nature of light laid the foundation for how we understand photography. What are you waiting for? Let's go there. Part 1, Hertz's discovery. Let's say visual animation of the reenactment of Hertz's experiment with a spark gap transmitter and receiver. Perhaps a historical picture of Hertz. Back in 1887, Heinrich Hertz concluded his experiment. He conducted a series of experiments that would forever change our understanding of the universe. He wasn't directly studying light for photography, mind you, but his discoveries were absolutely fundamental. They were foundational to photography. Hertz used a simple setup. He used an induction coil connected to 2 metal rods with a small gap. So at the top of the rod, a circular rod, there was a gap between them. It was acting as the transmitter, as you see on your screen. When a high voltage was applied, a spark will jump across the gap, generating what we know as electromagnetic wave. Why would something just jump by the application of high voltage? So that is how we discovered that it was actually electromagnetic waves, as we are going to see the character of this thing that is jumping. He then set up a detector loop, something that would detect this thing that is jumping. A simple wire, it was just a simple wire loop with its own small spark gap, almost like similar with a gap. A tiny spark would also jump across the gap in his detector loop when without any physical connection. There was no physical connection between his transmitter and the receiver. When the high voltage is applied, that same spark, as it goes across this one, it also goes across the other one. This was the first undeniable experimental evidence of electromagnetic waves propagating through space. Now let us look at visual graphics showing a simplified diagram of EM wave propagating from the transmitter to a receiver. Now, how does this relate to photography, videography, and cinematography? While Hertz's initial experiments focused on radio waves, the principle he demonstrated, which is the generation and the detection of electromagnetic radiation, is precisely what allows our cameras to function. Every time you press the shutter, you are essentially detecting electromagnetic waves in the form of light. His work proved that these waves exist and can travel through what was thought to be an empty space, carrying energy and information. Beyond just proving their existence, Hertz also showed that these electromagnetic waves exhibited properties strikingly similar to light and heat. They could be reflected, they bounce back. They could be refracted, bends, and even polarized, some of them removed. They are not just abstract physics principles or concepts, they are the very principles that govern how light interacts with our subjects, our lenses, and our sensors. Understanding reflection helps us control highlights and shadows. Refraction is the magic behind how our lenses focus light. And polarization, well, that's a topic for another day, but it's crucial for things like polarizing filter. Now, if you see my kit, you see some of the polarizing filters in there. Now, think about it. The same invisible energy Hertz discovered, that is what we use today for our Wi-Fi. That is what we use today for our radio, even our wireless flash triggers in photography. Part 2, the properties of waves. Waves have measurable properties. 1 is the frequency, 2 is the wavelength, and 3, amplitude. Frequency, it tells us how fast the wave oscillates. Wavelength is the distance between the peaks. Amplitude is how tall the wave is, which in light translates to brightness. To visualize this, you can use a rope, wiggle it slowly, and you get long waves like red lights. Wiggle it quickly, and you get short, rapid waves like blue light. From head spark to the glass in your camera lens, the wave nature of light is at the heart of every image you capture.
This project requires a high voltage pulse in order to work, and we will obtain that pulse with a lighter like this. Here we have one that we have modified for our purposes. Let's open the lighter. Here it is. This is a piezoelectric element that produces a pulse of several thousand volts. There are these two wires that come from the piezoelectric, and we have connected these two wires in order to be able to get the pulse. Here we can see the spark jumping when we pull the trigger. This is our setup to replicate Hertz's experiment. We have the spark generator connected to these two wires, and the electromagnetic waves will travel through the receiving antenna. Here we have a neon lamp connected to the antenna, and when the spark is produced here, the neon lamp will glow. Okay, I will pull the trigger to generate the spark. And we can see the lamp glowing along with the spark. We are using now a high voltage power supply. This power supply outputs several thousand volts. The output of the power supply is connected to this capacitor. The capacitor stores the energy, and the spark will be more powerful in our transmitting antenna.
Creative vision, where sight becomes story.
See better, shoot better, create better.
You got the camera, now get the vision. Shoot with purpose, create with vision.
Creative vision, creative vision.
This is Creative Vision, where sight becomes story. Until next time, keep creating with vision.
Creative vision.
Witness the transformation.
Creative Vision.
See better, shoot better, create better stories.